All right, hello, welcome to another video here. We're going to talk about integration by parts. Okay, we've talked about the DI method. I'm going to further explore the DI method. We've done type 1 questions. So if you were following along with me in my previous lessons here, I taught you how to do the DI method, which is basically using the integration by parts formula or the expression here, integration by parts, in a chart method without memorizing the formula. You can use a chart, which is really handy. It's much easier. It's kind of like synthetic division, right? Like there's polynomial long division, then there's synthetic division. So the DI method is like integration by parts, a shortcut method like synthetic division. That's all it is. So here's the DI method here, and again, watch the previous video if you didn't quite catch that. But I would encourage you, just as a review, pause the video right now and see if you can do these 3 questions that I have up on the screen using the DI method. Okay, that's what we covered in the first video. So go ahead and pause right now, see if you can do that, and I'll show you the answers in a second. Okay, so here are the answers to those 3 questions using the DI method. And this is the DI method, what I call type 1. Okay, and what do we do in type 1? Well, in type 1, you focus on the derivative. You focus on the derivative column, and you stop when you get a 0 in the derivative column. So type 1 involves this right here. We're differentiating, and usually it is just kind of algebraic polynomial expressions, and we get a 0 in the derivative column. You see, that's for all of these types. So that is type 1. All right. Now, type 2 is a little bit different. Okay. So you might not get down to 0. It might be going for quite a while. You might not get down to 0, and you might be wondering, do I have to write all of these lines, like all of this? Do I have to do all this? Well, type 2, you can stop when you run into a row that you can integrate using other methods. Either it's easy to integrate by sight, or you can use substitution, you can whatever. So you can integrate a row. If you can stop and simplify a row and integrate, you can do that too. So remember in the DI method that each row in the chart expressed the integral. So that's why we put these two what would be functions here in the integrand. They're multiplied. We put these. I'm going to put this right here, x to the 4th, and I'm going to put ln x right here. And so each row represents an integral, each row. And it's when we start to stagger, so you look up here, right? It's when we start to stagger the rows like this, okay? That's when that's not an integral anymore. This is not an integral anymore. This is not an integral anymore. That's why I can just write them like this, okay? So we kind of bypass that. But if you take a look at a row, you express that as an integral. Okay, so enough of that. So let's see if we can figure this one out here, okay? So I've chosen my polynomial as just my what I'm going to differentiate. Give me a second. Okay, so normally we would do this, but when we get more complicated ones, it's a little less clear which I should differentiate and which I should integrate. So I want to show you this. If you start off like this, okay, like I wrote this down here, this is going to be easy to differentiate, the regular polynomial function. Ln x is going to be a little bit tougher to integrate, okay? If you think about that, the derivative of ln x is 1 over x. What's the integral of ln of x? Okay, wow. Right away we start to run into problems. So I can actually differentiate ln x easier than I can integrate ln x. Okay? So now in type 2, we're going to start to have to, like, it's not going to be a slam dunk as to which one should I differentiate, which one should I integrate. So I am going to erase this because I'm going to tell you that we should do ln x over here and we should do x to the 4th here. Now, how do we know that? I was going to share this with you right away, and I'll do that right now before we get going too far in this, okay? If you're wondering if we have 2 functions and you don't know really which one you should differentiate, which one you should integrate, use this little memory mnemonic, lie8, okay? So you're going to want to remember that. The L starts for logarithms, which is including a natural logarithm. Okay, and this is the order in which you differentiate. So if you have a choice between two functions and one is a log and one is not, you're going to want to put the log in the differential column. Okay, lie 8. What's next? Inverse trig functions is actually next. You think, well, we're going to give preference to inverse trig functions? Yeah, they're a little bit easier to differentiate than they are to integrate. We have charts and tables, right, for derivatives of inverse. So you're going to go inverse next. A stands for algebra or polynomial, so just algebra. And we usually, don't have logs or inverse trig, and usually algebra is the first one we run into, right, so far in our examples. And then trig, like regular sine, cos, tan, and then exponential functions, okay? So that's with the x in the exponent position, so like e to the x, okay? You would differentiate that last, you would integrate that first. Okay, so here we go, we got lie 8. Now we know which one we should differentiate, which one we should integrate. And so type 2, okay, so type 2, stop when you can integrate a row, okay? So if we differentiate here, it's going to be a while before I get to 0, maybe never get to 0, but I'm going to keep my eye on the rows that I make, and pretty soon you're going to see that we're going to be able to simplify a row, and it's going to look really easy. So the derivative of ln of x is 1 over x, okay? And I'm going to move over here to the integral column now. The integral of x to the 4 is x to the 5 over 5, okay? All right. Now, I'm noticing that each row is an integral. And if I put this off to the side here, look what I have. I have 1 over x times, and I'll just separate this a little bit. Okay? Well, this is a constant, which I can actually bring out to the front and just totally forget about when I'm integrating. And look at what I have left over. I have actually x to the 5 over x. What's that? That's x to the 4. So in this case, you do one differentiation, one integration, and now you look at the row and it simplifies. It simplifies. So now you can integrate a row. So watch what happens now. So I take this and I go, my first term, I am still going to do this sort of offhanded thing right here. Okay, sort of the diagonal thing right there. And I'm going to be left with ln x times x to the 5th over 5. Okay. Now I shift to an integral. So I have minus the integral of, this is actually 1/5, minus 1/5 the integral of x to the 4th dx. Okay. So I've actually done this. I can use an integral, a row, integral row. All right. Okay. Let's keep going. So because this integral is actually a little bit easier to integrate just by sight, that's why I used that. And I've actually got a 1/5 as a common factor here, right? 1 over 5, 1 over 5. So I'm going to take a 1 over 5 out. I'm going to be left with x to the 5th ln x. And then what is this integral here? Well, it's going to be minus. That's going to be x to the 5th. Wait, what did I do here? Yeah, x to the 5th over 5. Right? Because I took this out and then I integrated this. Okay, so I've got a 1/5 out plus c. Okay, x to the 5th. All right, everyone see that? So that's an example of type 2, the I method. When you can integrate a row pretty easily, you can just write that integral in there and then go from there. You don't have to continue with the chart. All right, type 2. Okay. Let's do another one. So here's another example here. The integral of x squared times sine of 3x. Okay, this is very similar to one we did before. I don't think we did the x squared here before. So what we're going to do is we're going to try and figure out which one we should put in the D column and which one we should put in the I column. So lie 8 gives us our indication of which one we should use first. So this is an algebra one. and this is a trig one. Okay, so we have a coming before t, so it looks like we're going to put x squared in the derivative column, and we're going to put sine of 3x here. Okay, and yes, this is very similar to what we had before. Okay, but we're gonna do this a little differently. This is going to be a type 2 type question. All right. So plus minus. Okay, so differentiate. Well, that's 2x. That's 2. Now, I can go to 0 here. But this is going to be a type 2, so we're going to keep our eye open for a row as well. Because, okay, let's just keep going. So sine of 3x, right? The integral of sine of 3x is going to be negative 1/3 cos 3x. Okay. Negative 1/3 cos 3x. I'm keeping an eye on my rows here. If I have 2x times 1/3 cos 3x, that's two functions still. That's going to be a little tricky. I don't think I like that. Let's go another one. Let's see what the other row tells us here. So what's the integral of negative 1/3 cos of 3x? That's going to be negative 1/3 sine of 3x, and again times 1/3, right? Because I have to counteract the chain rule there. So it's going to be a negative 1/9 sine 3x. Now, if I look at this row, okay, integral here, dx, I have a 2 times a negative 1/3 times a positive 1/3. So I really just have one function here. And I'm going to stop because this function, I don't like that yellow color, but this integral right here is actually the integral of, now we have minus, so it's minus, right? The integral of 2/9. Well, actually I can go 2/9 minus 2/9 outside even. And this is going to be sine 3x dx. Okay? So look at that. That is a nice easy integral for us to work with. Now you might be saying, well, Mr. Maxwell, I could have just done one more and then I wouldn't have had to do this integral. I have to do the integral anyways. Well, it's true, but you can see how this works for the type 2 question as well. Okay, so you don't have to do the integration here, but you do have to do it here, right? So what have we got so far? We've got, all right, let's jot this stuff down here. So I've got negative 1/3 x squared cos of 3x. Okay, and then I'm going to do this as well. I have to use this diagonal. So this is going to be plus, right, 2/3 x, 2/9 x, my apologies, 2/9 x sine of 3x. And then I have this, which is a minus 2/9 integral of sine 3x dx. So this one, we're really not saving ourselves much time with type 2 here because we have to find the integral anyways. But you can see how this is going to be the same, it's going to get to the same answer as if we filled in this last piece of this last row here. So I want to go ahead and evaluate this integral. Okay, so I'm going to leave all this stuff here. 1/3 x squared cos 3x plus 2/9 x sine 3x, and then I'm going to go minus 2/9, and the integral of sine of 3x is going to be times, what was that, 1/3 negative 1/3 cos 3x plus c. So my final answer then, I won't factor anything out here just so you can kind of see. I won't do too many things at once here. Plus 2/9 x sine 3x, and this is going to be plus 2/27 cos 3x plus c. Okay. Now, I know what you may be thinking. How does this relatively harmless looking integral turn into this monster right here? That's a valid question. But it's not as simple as it might seem on the outset, right? So yeah, that's how you do that. And you know what, integration by parts makes something that's actually seemingly impossible. It makes it quite doable. Okay? Okay, so that is the type 2, DI method type 2. And so what you want to remember for type 1 is stop when the derivative row gets to 0. Or type 2, you can stop when you can easily integrate a row. Okay, so that's type 1, and that's type 2 for the DI method.